Hello, this is the third part of this chapter 5.4, and we will talk about linear transformation from space V into itself. And this is just a simplified case of the case we look at the part 2 of this series. So we have a vector x, and we apply the linear transformation to get the image of this vector t of x. But we say that we also can go to find the easier basis to work with and perform this transformation in this easier basis to get the image of this basis in the appropriate coordinate systems B. And we also can go from between our image in our original coordinates and our basis. Because there is the same dimensions in the both image and the original vector, there is only one system of bases. So we call our transformation the B matrix for transformation T. So it's only one basis, so there's one matrix, one coordinate system. So things are a little bit easier now. But it's still pretty abstract, and especially the example which given in this chapter is quite complicated, so I'd like to go through it very slowly to get the main idea across. And here, like this is the main example for this chapter, is when we are using the linear transformation between the two spaces which consist of polynomial of the second degrees. So we have the set of polynomials which has the free term, linear term, and the second degree term, which can be written down as a0 plus a1 times t plus a2 t squared. And we apply the transformation which convert them into the polynomials which has only two terms, the coefficient a1 plus double coefficient a2 times t. And probably all of you recognize right away that what I'm doing here is actually taking the derivative. Our transformation t is just the derivative with respect of t. And that's kind of neat, but also very hard to work with. Much easier to work is just a regular space R3, when we can represent our second degree polynomial is just the vector of three components. First, represent the free term, second, first degree terms, and the third one is a coefficient in front of the square. So that's much more straightforward. And of course, our image will also be an R3 space, with a difference that because we don't have a quadratic term anymore, we took derivative. Remember, derivative always take one power away. So our third component always will be 0. Our first component will be the second component of our original space, and our second component will be doubled. Okay, so it seems like these two R3 spaces are much easier to work with, but how we can go between two? It would be much easier if we can go between two R3 spaces. And we know from the period chapter that should be some kind of matrix by which can be multiplied to basically do the same transformation. And this matrix, you know, I already told you that it's called B matrix for T, should have just basically the image of the basis vectors for our space R3. Okay, let's just try to compile such matrix, but and conveniently, we actually has been given basis for our R3 space, which consists of three basis vectors, 1, t, and t squared. We know that there can be a multiple basis. That's one of them. One of them is given us. So let's try to take these basis vectors and find their image. Okay, our first basis vector is b1 is equal 1, the second one b2 is equal t, and the third one b3 is equal t squared. Okay, nice. So let's now write it down in the as a three component vector, which means that we need to find our coefficient A0, A1, and A2. For B1, things are easy. That's a free term, no t involved. So only coefficient A0 will be equal 1, rest of them will be zeros. Okay, for B2 is equal t, so this is the linear term is equal 1. So A1 is equal 1, A0 and A2 should be 0. Finally, B3 is equal t squared. Again, we have a quadratic term only here equal 1, and the rest of parameters equal 0. So let's try to compile now when we are successfully convert into the our basis coordinates. Let's calculate the image. So the image of our basis vector B1 or 1 would be, you know, just the 0, because that's the only so when we take a derivative of 1, derivative of constant is equal to 0. So our T1 is 0. Okay, so how about the second vector, basis vector T? Again, we take in derivative of T, which is equal 1. So the image of our second basis vector is 1. So finally, image of T squared will be derivative of T squared, which gives 2T. So we has the third basis image vector. Now, though, we need to convert those basis vectors into the R3 coordinates. So we need to get a coefficients again, because we just need to have a set of 3 components. So we need to calculate again A0, A1, and A2 of our image vector. Okay, let's look at T1 is equal 0. So again, clearly it's equal 0. So all 3 components A0, A1, and A2 is equal 0. The second one, image equal 1. Again, this is just a free component. So A0 is equal 1. Linear term and quadratic is 0. So finally, the third vector, 2t, so it's just a linear term, and this linear term A1 is equal to no free term, so A0 is equal 0, and no quadratic term, so A2 is equal 0. Okay, now let's switch from our coefficients to actual vectors. So our first basis vector written in B coordinates is 0, 0, 0, our three components. For the our second basis vector T written in the B coordinates is A0 is equal 1, and the rest is 0. Finally, our third basis vector written in B components will be A0 is equal 0 first component, A1 is equal 2 second component 2, and A2 is equal 0 third component is equal 0. Okay, so now when we actually have our 3 basis vectors in the B coordinates, we are done with our matrix. All we have to do to compile the B matrix is just put them row by row. First vector, zeros, second vector, 1, 0, 0, and then the third one. And we set them down. However, we also ask to confirm that the matrix we find is actually correct. And we will know that it's correct if we multiply this matrix by the vector, some given vector, general vector P in the coordinates B, and we will get the image of this vector in components B. Let's just do exactly that. Let's take a general vector P of T, which of course will be represented but in R3 space by the vector A0, A1, and A2. And let's find image of this vector in the B coordinates. And again, it will be just the derivative A1 plus 2A2. And in the our basis component, it will be a vector A1 to A2, 0. So, okay, so is that vector will be the same as product of B matrix for T by the our vector P in B component? Let's try. Let's write down our matrix TP. and multiplied by, again, our general vector PT has 3 components, A0, 1, and 2. Okay, let's just do the product of matrix and the vector. So our first row multiplied by the common column will give just the first value, A1, which would be exactly the same as in the previous column. Our second row by the vector will give us 2A2, exactly as we expected. And finally, our third row by the vector, because third row is equal 0, should give us a 0. Indeed, we started with our image in the B coordinate, and we end up with the same result as the product of our matrix in B component and our vector in B components. So this method seems to be working. Okay, this is, now I would like you to go at the end of the chapter and try to solve a couple more problems to be comfortable with this kind of problems. This is pretty deep chapter, so you probably need to practice a little bit more than you did before.